A small team ships a support assistant in March. By June, the bill is $14,000 a month. Nobody did anything reckless. Every request goes to the same top-tier model. That model is good, and nobody wanted to think about it twice. Then someone reads the logs. More than half the traffic is, where is my order, and how do I reset my password? Most of that money bought nothing at all. By the end of this, you will know exactly how to stop paying it. For about 2 years, the default was simple. Pick the strongest model available and send everything to it. People started calling that Tokenmaxxing. Buy the biggest engine, never think about the load. And it felt like the responsible choice because the failure it protects you from is loud. A bad answer to a customer is visible on Monday morning. An oversized bill is invisible until the quarter closes. So teams optimize against the loud failure and eat the quiet one. There are 2 more reasons this sticks. The first is that one model is one line of code. No config, no branching, no second provider to keep credentials for. The second is visibility. Your provider bills you per key, per month, as one number. It does not tell you where that money went. $11,000 of your $14,000 went to easy requests. A model costing 1/50th as much would have answered them identically. You cannot cut a cost you cannot see, so nobody cuts it. Model routing is the fix, and the idea is small enough to say in one sentence. Before a request reaches a model, you look at it. You decide how hard it actually is. Then you send it to the cheapest model that can do the job. If that model struggles, you send it up to a stronger one. That is the whole pattern. 4 moving parts make it work, and we will build them one at a time. Part 1 is task classification. A classifier takes the incoming request and returns 2 things: a label saying which tier should handle it, and a confidence score between 0 and 1. There are 3 ways people build this: rules on keywords and request length, which is crude but nearly free. A small trained model over the text embedding, which is what most production systems use, or a cheap model prompted to grade the request. That grading call typically adds 20 to 200 milliseconds. It costs a small fraction of 1 cent. Part 2 is tiers. A tier is just a price and capability band you have decided to treat as one bucket. Today, the budget tier runs 10 to 15 cents per million input tokens. Mid-tier models sit at $2 to $3. Frontier models run $5 to $30. Their output tokens are more expensive again, often 3 to 6 times their input price. So the spread between your cheapest usable model and your most expensive one is commonly 30 to 50 times. That gap is the entire opportunity. Part 3 is escalation, sometimes called a cascade or a fallback path. You try the cheap model first, then check the answer before you return it. The checks are ordinary engineering. Did the output parse against your expected schema? Did the model refuse or say it does not know? Did the classifier's confidence sit below your threshold? Any of those trips, the escalation and the request is rerun on a stronger model. You pay twice on those requests, which is fine, because they are the minority. Part 4 is semantic caching, and semantic is the important word. A normal cache matches on exact text. So how do I reset my password and I forgot my password help are 2 separate misses. A semantic cache converts each question into an embedding. That is a list of numbers that encodes meaning. It then looks for a stored question whose vector sits close by. Close usually means cosine similarity above about 0.95. A hit returns the stored answer in about 10 milliseconds and calls no model at all. Now watch one real request move through all 4. A user asks how to change the shipping address on an open order. The cache is checked first and misses because nobody asked this today. The classifier reads it, sees a short factual lookup against your documentation, and returns the small tier with high confidence. The budget model answers using 800 tokens of retrieved context. Output validates. The answer goes back, and the question and answer are written into the cache for next time. Second request, a user pastes 2 invoices and asks why the totals disagree by $412. That is multi-step numeric reasoning over messy input. The classifier flags it above the small tier immediately, so the cheap model never sees it. Suppose your classifier had been wrong and routed it low. The small model returns an arithmetic answer. It fails your check against the invoice totals. The escalation fires, and the frontier model produces the correct reconciliation. You paid a little extra, and the user still got a right answer. Put numbers on it. 100,000 requests a month, averaging 1,000 input tokens and 300 output tokens each. Send all of it to a frontier model, and you pay about $1,250. Now route it, and assume 80% lands on the budget tier. That 80% costs about $26. The remaining 20% still costs $250. Your total is under $300, and the hard requests were answered by exactly the same model as before. You do not have to build all of this yourself. LiteLLM gives you one client interface that speaks to many providers. Switching a request from one model to another becomes a config change rather than a rewrite. It handles the routing rules, retries, per-key spend limits, and fallback ordering in that config. The problem it solves is lock-in and plumbing. It does not decide which requests are hard. You still supply that judgment. RouteLLM comes at the other half. It is a learned router. Instead of you writing rules, a model predicts how likely a query is to need the stronger model. That model is trained on human preference data. You then set a threshold for how much of your traffic goes up. In the original research, it held 95% of the strong model's benchmark quality. It sent only 14% of queries to that model. Treat that as proof the technique works, not as your number. Your traffic mix decides your number. OpenRouter takes the marketplace approach. One account and one API surface sit in front of a large catalog of models from many providers. Prices and availability are exposed, so you can select or fall back across them at request time. The problem it solves is access and redundancy. A provider is degraded, or a cheaper equivalent appears next month. You are not blocked on a new contract and a new integration to use it. For the caching layer, you have tools like GPT Cache and the cache modules built into gateways. They do the embedding, the vector lookup, and the eviction for you. Two things to keep straight. This is not the same as the prompt caching your provider offers. That discounts repeated context but still runs the model. A semantic cache skips the model entirely, and it fits workloads with repetitive questions. On genuinely novel traffic, your hit rate will be near zero. Now the honest part, because routing is not free. The real risk is misclassification. A hard query routed to a weak model does not usually fail loudly. It returns something fluent and wrong. Your escalation only catches it if you wrote a check that can detect it. Schema validation catches malformed output. Nothing catches a plausible wrong number unless you compare it to something. So the strength of your routing is the strength of your checks, not the cleverness of your classifier. There is also latency and maintenance. Every layer you add sits in front of the user. A cache lookup and a classifier might add 50 to 200 milliseconds. An escalation means paying a second round trip on those requests. Then models change. A new version ships, prices move, and the thresholds you tuned in spring are wrong by autumn. You are trading engineering complexity for money. On low volume, that trade is not worth making. So the takeaway is this: quality never came from always using the biggest model. It comes from matching the model to the task. Routing is just the mechanism that makes that matching automatic instead of manual. Classify the request, send it to the cheapest tier that can handle it. Escalate when the answer fails a check, and cache what repeats. Start by logging which of your requests actually needed the expensive model. Most teams are surprised.